Alright, so what's awesome is we already did the recap on everything. Where's my microphones? Oh, so good. The other room I teach in, the microphones don't work, and it seems silly because this room's small, but I literally use a microphone in my high school classes too now, because talking for 6 hours straight just is exhausting. Something's lying to me. Alright, so, hey, there you go. This is my Physics 1 class. Do y'all remember these things? Does this bring back good memories? Obviously, I'm not testing you on this. This is Physics 1, but just so you know that what you've made it past, this is in the past. Unless you have to study for the MCAT at some point, then it'll be in your present. But let's go ahead. Let me get a PowerPoint open. Today is going to be all about me just kind of solving problems, making up problems on the fly, grabbing problems from the problem sets, all that kind of jazz. All right, so we'll just call this Test 1 Review. All right, so unfortunately at this point, there's only two. Let's pull them open. So if we go down to like the electric field vectors one, let's see, you all probably solve this. So this one is a great problem. So, let's maybe make we have that one and that one. Let's see, what problem can we make up with vectors real quick? A square and a triangle, I don't want to get too crazy. How crazy do I want to get? So let's just steal this thing, because it's all nicely formatted and everything. Y'all tell me, where do you want me to move the charges around? Let's slightly modify this problem and solve it. What do you all want me to do? Where do you want them to be? How wild do we want to get? How can we modify this? What can I change? Literally anything is free game. You know what? Let's move this one up here. Let's move the negative one up here. And let's find, again, we're going to see how much how much math we're going to want to do today. Change the numbers. Let's call this one 7. Let's call this one, give me a number between 1 and 10.
6.
Good. Oh, it's already 6. Different number, that's not 6.
4?
4 it is. Great. What about this one? You know what? Let's make it 15. All right. How mean do I want to be? Find the force on the -4 microcoulomb charge. There you go. This is going to be a good... So I've already drawn the picture for y'all, but the next step, draw the direction of, so see if you can draw the forces that are acting on that charge. Try it out, y'all. And again, I will upload this PowerPoint after the class. So don't feel like you need to copy everything down. So first step, draw the forces acting on it, kind of like a free body diagram. So the key to this is you break it into pieces. So we'll do, and let's just number these. We'll call that 1, 2, and 3. Make our lives a little easier notation-wise. So 1 on 3, it's going to attract force 1, 3. And then 2 on 3 is also going to attract. Now we have to figure out, 1, what these forces are, and then we have to remember x components and y components. So this problem basically boils down to, sum of forces in the x, sum of forces in the y. Yeah, we're gonna have to do all that. So, but for now, let's just calculate F13. What's the equation? See if you can figure out the equation for the force acting on 2 point charges. That's the next step to kind of think about. You know, we could have written all our givens, stuff like that. You know what? I'll do that while you all find that equation. Our givens, we got Q1 equals 7e minus 6, Q2 equals 15e minus 6, Q3 equals negative 4e minus 6, R13 is 3 meters, and that's kind of all the givens so far. We will write down more givens for sure. Step 2, we're solving for F net. Step 3 was kind of where I left y'all. And I'm going to give myself room because there is another given we need to write down. So hopefully you found F, hopefully y'all are feeling pretty kosher about this. The Q's over R squared. Absolute value of the Q's. Remember, when it comes to vectors, do not put the signs in there. Don't put pluses and minuses in there. It's going to mess things up for you later on. It's better to do the directions later. So, F13, and then we'll sum up our forces in the X and we'll sum up our forces in the Y. So F13 is going to be K, absolute value of Q1, absolute value of Q3, all over 1/3 squared. That's easy. We have all that information. F23 is going to be K, absolute value of KQ, or Q2, absolute value of Q3, all over R23 squared. And this is where we see there's one more given we need to find. Give y'all some seconds, see if you can figure out. Looking at those equations, there is one variable in there that we have not written down yet. And then think about how would you find it. So again, we have K, we have Q1, we have Q3, we have R13. We have K, we have Q2, we have Q3. We don't have R23. So spend a few seconds. How would I find that? What does that represent? Where is that on my picture, R23? What is that variable representing? It's representing this distance. This is R23, the distance between those. How would I find that? R23 is going to be the square root just give myself a bit more room so things don't get too messy. Square root of 2 squared plus 3 squared, which equals something. What's kind of cool here, I don't know, I may just do 4 squared plus 9, so 4 plus 9, it's going to be square root of 13. What's cool is it's going to get squared later on anyway, so that square root will go away. You'll see what I mean in a second. So I actually don't need to plug that in my calculator. But you could totally just plug it in your calculator and get the square root of 13. That would totally work. All right. So force of 1/3 is going to be 9e9 times 7e minus 6 times 15e minus 6 divided by 3 squared. That's going to spit out a number. This one's going to be 9e9 times 15e minus 6. Again, we're doing absolute values, so there's no positives, there's no negatives. And this is where I mentioned it's going to get squared, so it just becomes 13. But whatever. Because I don't want to confuse people, I'm going to go ahead and just put what this number is and just replace that with that, because I don't want people to... It's good to remember that you do have to square it. What I did there previously was correct. I wasn't breaking any rules. Nothing there was incorrect, but just to keep it matched up with how I've been teaching you up to this point, we'll just go ahead and get what that value is. All right. Cool. And those are literally just numbers. Nothing super exciting. Make certain the number makes sense. I'm multiplying two tiny numbers times kind of a big... You can add up when you're multiplying, you can add up the exponents, yeah.
For the force of 1 on 3, isn't it supposed to be 7e negative 6 and then 4?
Yeah, thank you. Thank you, great catch. And that is a very important... Now, the good news is if you made a mistake like that, so this would be the amount of steps we're doing here. This is on this level of free response question. I would not ask a question like this for multiple choice. Because, I mean, look how long it's taking us to solve it. This problem, if you're going through it carefully, takes about between 5 to 10 minutes if you know what you're doing. If you know what you're doing, it takes 5 to 10 minutes just writing everything out and being careful. If you don't know what you're doing, obviously it's going to take you longer. All of your free response problems should be solvable within 2 to 3 minutes. If you do the math, here's how the breakdown should be time-wise. We have 80 minutes total on this test. 60 minutes for the multiple choice, 22 questions, so just do the math. 60 divided by 22, you get a little bit less than 3 minutes per problem. And then that leaves you 20 minutes for the one free response problem. That's kind of how you want to pace yourself through this thing. That's my recommendation. So even when we're taking the test, when we get to the last 20 minutes, I will legit say if you have not started the free response, you probably want to start that now. All right. But yeah, good news. If you all did the mistake I did, and this is a free response, that would not affect the grade much. You'd probably get out of the 20 points, somewhere, depending, if that was the only mistake, you should get 17 or 18 points out of 20. If everything else is perfect, because it's a silly mistake. That's the beauty of free responses. You actually get graded on what you know, not on silly, if I could somehow do it, I would make the whole thing graded on your all's the work that you show, but the reality is there's no way that the grader has time for all that. So, all right, let me just write this carefully. 0.028 newtons. And then we just repeat that with the other one. Replace that with that. 0.042 newtons. Okay. And if you just add those two numbers, you get the wrong answer. All right. They're vectors, y'all. So we're going to take this whole nonsense, and we got to move on to another slide so I have the room to do this. This is also why you get an entire sheet of paper for the free response, so you have room to show your work. So if we look at our picture here, this one, that's good to go. We don't need to do anything with F13. It's already in the X component. This one, F23, we have to break into X and Y component. Now, unfortunately, we're going to have to do a little bit of work before we can get to that point. So if we look at F23 on this picture, F23 is here. We need this angle. We need this angle to be able to find the X and Y component. So F23, if we can find this angle, then we can find its X component, so F23X, and we can find its Y component, F23Y. How do we find that angle? I'm going to give you all a few seconds, see if you can think through how would you find that angle. Given the information in this picture, how could I find that angle? And this is where you'll remember your trigonometry. I have similar triangles that share an angle. If I just connect that, you can see I have a big old right triangle that shares that. So I have this big old triangle with a side of 2 meters and 3 meters. I can find the angle from that. I have two similar triangles that share an angle. So it's going to end up being that the angle is tangent inverse opposite over adjacent. And I'll just write it. So tangent of theta equals opposite over adjacent. So theta equals tangent inverse. What's my opposite? 2. What's my adjacent? 3. And that spits out an angle. 33.69. And so if I want the x component of that, that's my adjacent side. So again, I'll let you all think, feel free to kind of look this through, but for now I'm just going to straight up tell you that the x component is going to be f23 times cosine of theta. f23y is going to be f23 sine of theta. Not because the x and y component not because the x component is always cosine, not because the y component is always sine, but because if I have this angle, the adjacent side is the x. So, toa. So if you solve for the adjacent side, use cosine. The opposite side is the y component, so I use sine. It always depends on the angle that you have. So you just plug that on in. We just had the values for f23. That was 0.042 times cosine of 33.69. 0.042 times sine of 33.69. Move my whole picture up so I have room to put the answers. And that equals things. Make certain your all's calculators in degrees mode on the test. It'll be very sad if your calculator's in radians mode. All right, 0.042 times sine of 33.69. That equals 0.0233. And why did we do all of this? We're almost there, y'all. We're almost at the end. I know it's a lot of steps. We needed to sum our forces in the x. So don't forget, y'all, not only is F23x chilling right here, but I'm just going to shove this thing. We also had F13. That was there the whole time. So my sum of forces in the x. Now, very important. Right is positive, left is negative. Right is positive, left is negative. So, F13. Positive or negative, y'all? You tell me. Negative. Very nice. It is pointed to the left. So I get a negative F13 because it's pointed to the left. Plus x component of F23. Left or right? Positive or negative? Negative as well. It's also pointed to the left. It's a little hard to see because it got covered up. But there it is. It's pointed to the left. So I get a negative F23. And we just put in the numbers. 0.028. Negative plus negative 0.035 equals a number. .063 newtons. So I added up my forces in the x. Now we're going to add up our forces in the y. Good news is, and I should have put an x here. Should have put that little x here. There's literally only one force in the y direction. There's literally only one force pointed up or down. And it's F23y. Is it pointed up or down? Down, positive or negative? Negative, spot on, y'all. Boom, there it is. All right, and there's a couple last steps before we're done. I have my force in the X, I have my force in the Y, but the problem didn't ask for it to stay there. I need my net force. So, again, I'll give you all a few seconds. If I have an X and I have a Y, how do I find the net force? What am I going to do? F net equals what? If you said that we should add them squared, you are correct. Now, I will tell you all, in this case, it doesn't actually matter whether or not you put them as positive or negative because they get squared. But it's good to get in the practice of that. So we get the square root. And actually, I'll just do this on one last slide. Because I'll need some more room anyway. Okay, so we had negative 0.063 squared plus negative 0.023 squared and you get 0.067. So that is my net force. Now, unfortunately, this won't be the end because there's one more thing I would like for us to do, and that's find the direction. So we had F23 going this way. And we had F13 going this way. And now that we actually know the numbers, let me make these arrows actually appropriate. So F13, we calculated this before, was 0.028 newtons. F23 was 0.042 newtons. The size of the arrow corresponds with how big that force is. The bigger the number, the bigger the arrow. There's a reason why I'm saying all this. So, this one's bigger. F23 is bigger, so it should have a bigger arrow. There's a reason I'm doing all this nonsense. So this one will be bigger than that one. Why am I doing this? Because we are about to find visually the net force. So this is something I did way at the beginning. If you have two arrows, and this is maybe something you learn in Physics 1, you can do all the math. And we're going to do the math to find the angle. But one of the things you can do, you can take them and do tip to tail. So if I take F23, and that one is down to the right, and then I draw F13, and I put that right here, this is the direction of F net, tip to tail. And what we're going to find right now is this angle. The last step is to find the direction. How do you define direction? By an angle. How many degrees is it above, below various axes? How do you find that? We got a triangle, y'all. We have F net X. We have F net Y. So, theta is going to be tangent inverse of Fy over Fx, which equals tangent inverse of the negatives, again, are going to cancel out, but whatever, I'll put them in here. Negative 0.023 divided by negative 0.063. And this is the last step. This is the very last step. 0.023, again the negatives cancel, 0.063, and I find below the negative x-axis. I find that, all right, great, I figured out how big the arrow is. Now I know which way it's pointed. It is pointed 20.05 degrees below the negative x-axis. Negative x-axis points to the left, that's what I'd say. Now, if there is a problem like this in the test, I will also say you can just kind of draw a picture and kind of say, bam, it's that. Okay? Both of these are correct. Drawing the vector and labeling it with the angles and all that jazz, that's good. But I can almost guarantee you that if I ask to find a vector, I'm not only going to want how big that vector is, I'm going to want the direction of it, i.e. the angle. So be prepared for that. Make certain you're comfortable with this last step. We probably spent a lot of time doing this first, all the mathy things. The angle one is also important. It's a vector. Direction matters. Okay. So, great problem to kind of work through on your own. The whole solution's here. So if this is something that you're like, man, I don't know this is an area that I feel weak in, before Thursday, try to solve this problem. I will post this. So what I just did will be posted. Try to do it without don't just look at the solution and say, yes, that makes sense. Try to solve this one without the worked out solution right there. Only use it if you're stumped. Mimic the test situation as much as possible. All right. Let's do some more vectors, but no math. Let's spare ourselves some math. All right, so this one I'm just going to draw some things. Draw the direction of the net electric field given the at the point shown below. Okay, we're going to let's get all sorts of funky here. All right, let's put a negative charge here. Let's put a positive charge here. The size of these charges will say corresponds to how big they are. So okay, for this one, draw the electric field here. This is legit one of the clicker questions. So that's the first one we'll start with. See if y'all can figure it out. Draw the direction of the net electric field at that point. Try it out. So whenever we're considering vectors, you do one at a time. So we're not finding a force here. There is nothing located at point P. It's just a random spot. Remember this whole idea of electric fields, it's a made-up thing. So first we consider the positive charge, and we say electric fields point away. Let's just call that 1. So that's the electric field due to charge 1. All right, now that you all have that one, see if you can get the second one if you haven't already. I found the electric field due to number 1, but to get the net field, I need both of them. So electric fields point away from positive charges. Which way do they point for negative charges? Away from positive. They point towards the negative, but you have to be very careful here. The size of these arrows matter. So we remember we're not going to do any math here, so I'm about to show you some math, but we're not going to actually use this math. E equals KQ over R squared. The closer you are, the smaller the R, the bigger the field. So the electric field too is bigger. It points towards the negative charge and it is bigger. So if I want the net field, I add those together. How do you add those together? Again, you can kind of be tip to tail. There's electric field 2. I start the red arrow where that one ended. And my net field points from the beginning to the end. E net. There you go. So the net field points to the left. How much? You would need numbers. But all I care about for this problem was that you understood distance mattered and the direction of electric fields. All right, let's get spicier. Let's put a positive charge here. Let's put a negative charge here. Find the electric field there. Find the net electric field. So same thing, one at a time. So the electric, we'll just again call that 1 and 2. Call them whatever you want, but let's just make my life easier. Points away from that guy. Points away from the positive charge. And it's going to point towards the negative charge, and this is where you have to be careful. It may not be super obvious here, but the negative charge is farther away. Because if you made this a triangle, if you made this a right triangle, the hypotenuse is always the biggest side of that triangle. Subtle, but it is something that shows up here. All right, so again, tip the tail, y'all. We draw E1. We draw E2 down and to the left. The net vector points from the beginning to the end. If you're ever adding vectors, this is how you can do it visually. There you go. Good old vector practice, but no math required. So questions like this may be more aligned with multiple choice kind of questions. It is not time intensive, but it does check conceptual understanding. Do you know that electric fields point away from positives? Do you know that electric fields point towards negative? Do you know that electric fields get weaker the farther away you get? Do you know how to add vectors together? There's 3 concepts all at play here. If you're missing any one of those, you won't be able to get the answer. And depending on the multiple choice problem, maybe it's just testing one concept. Maybe it's testing a couple together. All depends on the question. Okay? Yeah?
Does it matter how you do the tip to tail?
No, that's a great question. In fact, let me show you the other way. Let me show you. So the question is, if I did like E2 first and then E1 after that. Yeah, so if I did E2 first, assuming I do a good job of drawing this, and E1, as long as I draw them consistently, we get the same size arrow the same way. As long as I do a good job drawing my arrows. Yeah. That's a great question. Addition, 2 plus 3 is the same as 3 plus 2. Vectors, when you're adding them, they should follow the same rules. What? Great question. Glad you asked it. Again, it's not perfect because I made my red arrow a little bit too big here, but there you go. All right. Cool. Okay, so that's good vector stuff. We love it. So much fun. Remember, electric fields and forces are not the same thing. A lot of people get mixed up on that. All right, let's do another question that could be multiple choicey. So, sure. I have two charges a certain distance apart. If I double one of the charges and half the distance between them, what happens to the force experienced by the charges? I have two charges certain distance apart. Because I'm so you know what? It doesn't matter. It doesn't matter whether they're positive or negative. Does not matter. Can make it two positive charges, can make it two negative. Tell you all, for this problem, doesn't matter. Two charges certain distance apart. If I double one of the charges and I half the distance, what happens to the force? So what this question is testing is, do you understand the equation that gives me the force due to two charges? Do you understand how it behaves? And there is a I love you've hopefully seen I ask these questions a lot. If I double this, if I triple this, if I half this, if I triple, hopefully you've started to recognize they all are solved the same way. They all get, there is a process to solving these, and no matter what kind of problem I give you, it's always the same process. Now, one strategy you can so first, what's the process? You find the equation that has the variables that you want and the one that's being affected. You isolate the variable that is, so in this case I'm saying what happens to the force? It's already isolated. But in other times you may have to move things around. In other cases you may have to move things around to figure out what happens. Now, you have options here. I'm going to show you all how to do it without plugging in any numbers. And I'm also going to show you that you can make up numbers. So let me show you the way I've been teaching up to this point where I don't. So this is my original. So where we don't have to do any math. I mean, I guess you have to do a tiny bit of math. My new force, K is always K. One of my charges is doubling. So I put a 2 in front of it because it's doubling. The other charge stays the same. And you have to be very careful with this equation. The bottom is squared. Whatever you do to the bottom also needs to be squared. So, you do the math, or I say do the math, you pull it to the front, so the 2 gets pulled to the front. Let me just go ahead and do the bottom. So the bottom there is K, Q, Q, whatever, they're absolute values. That's 1/4 R squared. Dividing by 1/4 is the same as multiplying by 4. Long story short, it's 8 times bigger. Okay? So, whatever happens to the bottom, if it's squared, whatever happens to it also needs to be squared. And I'm going to prove this to you all by showing you another way you can go about solving these problems. And it's by making up numbers. So, in a problem like this, it shouldn't matter what the numbers are. So let's just make up some numbers. In fact, let us make up the easiest number we can think of mathematically. If you're doing multiplication and division, the easiest number we can think of is hopefully 1. So let's just make everything 1. Q1, that's 1. Q2, yeah, that's also 1. Distance, yep, that's also 1. So if I made up all those numbers and just said everything's 1, that's 1, that's 1, that's 1, everything's 1. I get K times 1 times 1, divided by 1 squared. Bam, I just get K. Great. All right, now let's go ahead and play around with what happens if I do the things it says in the problem. So again, there, let me skip this on over to the other side. So this is one way of solving it. Let's go ahead and separate it so we don't get confused. So the second way is just make up numbers. In my second equation, I need to do what it says. I said I'm going to double it. What's 2 times 1? 2. That one stays the same. And on the bottom, what's half of 1? It's a half. If you do the math, you get 8 times k. Look at that. So, if I ever give you a problem where I say, hey, this does this, this does this, this does this, and you're like, man, I really don't like this whole variables playing around with thing. I like numbers. Make all your numbers 1. If a number doubles, 1 times 2 is 2. If a number halves, 1 times a half is a half. If a number thirds, it's 1/3. You can literally make up numbers for these, and that also works. So, 2 strats. And k is a number, so whatever. You get to see it's 8 times bigger. That's what matters. All right, cool. And again, we saw this with like capacitance. I said, hey, on the quiz, I think I did like the dielectric constant thing, and I said, this one's this one's this. How's the area compare? You can do this. There's a lot of problems like this that I've done. Okay, let's see. So, I've done vectors. I think that was the classic. Let me pull open the survey on my phone and see if there's anything specific that anyone added to it that you all wanted me to go over. So, let's see where I put that survey. Fingers crossed. Oh, so good. All right. So, I see capacitors, answers that have a variable left in them. I think that covered that. Vectors, good. What topics are we supposed to have? Vectors, conceptual vectors. Oh, okay. I see some potential energy ones. Sure, let's do that one. Vectors and vector. Well, we love vectors, don't we? All right. A proton is placed in a potential difference of, give me a number. 340 volts. Perfect. How fast will this potential be going in due to this potential? And you know what? We're going to do a twofer here. So a proton is placed in a potential difference of 340 volts. How fast will the proton be going due to this potential after traveling through? Let's use better terminology. Okay, so there's a twofer here. 1, so potential difference. Potential difference, that is just another word, i.e. voltage. Potential difference is voltage. It is a difference because the proton is starting at some voltage and then there's another voltage somewhere else. Now, what I want to propose to you all, if this is 0 volts, let's make this 340 volts. You subtract those two numbers, you get 340. Where does the proton start here? Will the proton go from 0? Will it want to go from the 0 to the 340? Or will it want to go from the 340 to the 0? Yeah, so a proton is going to want to be placed here, and it will experience a force that way, causing it to speed up. an electron will actually go the other way. Now, an electron is not given in this problem, but that's just a good reminder to you all. Protons go from high voltage to low voltage. Electrons go from low voltage to high voltage. In both cases, I'm going from a higher potential energy to a lower potential energy. All right. And remember, y'all, if you ever see the word fast, velocity, speed, conservation of energy. Conservation of energy, potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. I've already told you all that all these problems boil down to QV equals 1/2 mv squared. But let's go ahead and look at, I'm going to fill in the gaps for why that is. You know what? Maybe we do this just to be clear. All right. So why do they all boil down to this equation on the bottom, basically? All right, we're going to say my thing's not moving in the beginning. So actually these terms are going to go away. We're going to say it starts at rest. The potential energy initial is Q times V initial. That's going to equal Q times V final plus 1/2 mv final squared. Well, if we look at this picture, this is the final, this is the initial. That term's going to go away. The final voltage is 0. So it boils down to QV equals 1/2 mv squared. Every single one of these basically boils down to that. Okay? That change in voltage speeds it up. And we get that equation at the bottom. All right. And let's do this like I do my high school classes. There's one more thing you need. So you need to know the mass of an electron. So I'll jot that down somewhere. Mass of an electron equals, I'm fairly confident it's 9.11 times 10 to the minus 31 kilograms. Am I confident enough? No.
Are you in a proton or an electron?
Ooh, good point. Yeah, I put totally the wrong one. That was an electron. Yeah, good point. So let me get my formula sheet out. We actually need the mass of I'm so used to doing electron. Proton is 1.67 times 10 to the minus 21. All right, charge of a proton is 1.6 e to the minus 19 coulombs. And just a reminder to y'all, these are given in your formula sheet. There it is, 1.67 to 10 to the minus 27. There's that one. All right, so, I said I'm going to do this the way I would do my high school classes. I'm going to put the answer up here, so I'm going to quickly solve it on my calculator. I will work through the steps for y'all. But to give you all a chance, because the reality is, this should be times 10 to the minus 27. I don't know why I put a 1 there. Even though I don't want to be testing you all in algebra, and thank goodness y'all, I made up the numbers for this. It would have been possible for us to have broken the laws of physics if I'd made the voltage too big. Thankfully I didn't. Pro tip, you should never get a velocity higher than the speed of light. Thankfully we didn't get that, so yeah. Anyway. So the answer is 2.55 E 5 meters per second. And I'm going to double check. Boom, 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 boom. Good. All right, I will work through this. But try it out, y'all. Because part of this test is, can you solve these problems? The multiple choice comes down to you have to be able to get the right answer on your calculator. The free response, if you make an algebra mistake, not a big deal. The multiple choice, it is a big deal if you mess up the algebra. It is a big deal if you can't plug it into your calculator correctly, because you will need to get one of the answers that's shown there. And pro tip, y'all, you can always check your work by literally just plugging it back into the equation. Yeah, cool. Both sides of the equation should equal each other. So I just checked my work by literally taking my answer and plugging it in for that and making certain the right side and the left side equal each other. Fun fact, y'all, your algebra skills, you're like, ooh, I don't know how I feel about algebra. One of the multiple choice question answers will be right. You can literally just start plugging them into the equation and see which one works. So I'm going to give you all a few more moments, but I'll kind of break down just to plug in the numbers of what I did here. So 1.6 e to the minus 19 times 340. Ugh, there's not enough room. Equals 1/2 times 1.67 e to the minus 27 times vf squared. And then it's just algebra. Simplify the right side, divide it over, and then square root the whole thing. All right. And I think that kind of covered, that seemed to have covered most of what people asked. Any questions, y'all? Anything else you want me to specifically focus on? We got time. If y'all can't come up with anything, I'll come up with stuff. So don't worry. Does anyone have anything any type of problem you could think of that you're like, ooh, do that? Yeah.
Just the capacitors stuff.
Sure, yeah. Let's do some capacitors. So one of the things that, you know what, we'll do the classic. We'll do all three scenarios to figure out what stays the same. I asked the 3 clicker questions on that. I mentioned it during the review. I buy a capacitor from China, and it ships across the ocean after they did a bunch of testing with it. What variable is the same when it was in China and when it reached me? It sounds like a stupid question. Most electronics come from China, so this isn't even this is just the reality. Electronics, you buy electronics, a lot of it comes from China because they produce a lot of it there, and it's very cheap to buy. What variable having to do with, and technically there's a few options here. Let me go ahead and give you the options that would be presented to you. Is it energy stored? Energy stored in capacitor. Is it the voltage of the capacitor? Is it the charge in the capacitor? Or is it the capacitance? Which of the following will be the same? I'll give you all some time to think through this. So this is one where we can go one by one. Energy stored in a capacitor is 1/2 Q times V. And this is actually going to kind of reveal some stuff. Who knows how much charge this thing has? They charged it, they discharged it, who knows? So is the charge the same? Nope. which means the energy stored, nope. Voltage is based on what it's connected to. It is currently not connected to anything. So voltage doesn't stay the same. Voltage is based on how much charge is on it. Also, based on whether or not it's connected to a circuit. So the key punchline here, really the way you should think about this, capacitance. Remember, capacitance, y'all, is based on its area and the distance between the plates. Assuming that capacitor didn't get destroyed on the way over, this is literally written on the outside of the capacitors. 5 microfarads. If I buy a capacitor from the store and it says 5 microfarads, it better still be a 5 microfarad capacitor when I get home with it. Otherwise, yeah. It is a quality of the capacitor. Regardless of whether it's been, as long as it hasn't been blown up, as long as I haven't changed the area of the plates or the distance between the plates, as long as I haven't changed those two variables, you're good to go. All right. Let's do the other two scenarios. I hook up a capacitor to a 1.5 volt battery. After which, okay, I later disconnect this capacitor and use a different capacitor with the 1.5 volt battery. What variable will these two capacitors have in common? So I hook up some capacitor. You know what? Let's just make up a number for it. It's a 3. I don't want to find the symbol for micro, so it's getting milli. 3 millifarad. This one will be 8 millifarad. Same options. Will the energy stored be the same? Will the voltage be the same? Will the charge be the same? Will the capacitance be the same? One of these is very easy to rule out. It's capacitance. It's definitely not correct. I mean, one, I've already given you a problem with capacitance. But more importantly, I literally told you they're two different numbers. So that's hopefully obvious. The definition of capacitance is how much charge I can store on it per voltage applied. So if they have a different C, but they're hooked up to the same battery, they're going to get different amounts of charge on them. And then kind of subtly in that, I kind of said the answer. If they're hooked up to the same battery with the same voltage. So the answer ends up being voltage. A capacitor, if you have a circuit with a single battery, if it's only connected to one thing, whatever that one thing is, it gets that voltage. We also use that with resistors. The energy stored is not the same because, U equals 1/2 QV. Q is different, V is the same, so it's going to be different. So, all right. Process of elimination. The next one answer is going to be obvious, but make certain you can kind of think about why this is going to be true. I hook up a battery or a capacitor to a battery and fully charge it. I then disconnect the battery and throw it across the room. What stays the same without destroying it? Is it the energy? Is it the voltage? Is it the charge? Or is it the capacitance? All right, so let's go through our options. Is it capacitance? Well, I didn't change anything about I did not change the area or distance. So yes, the capacitance stays the same. The charge. Remember, a capacitor is literally like a bucket that instead of filling it with water, you fill it with charge. If you charge it, as long as you have not discharged it, it does not matter what you do with this capacitor as long as you don't discharge it. I could change the area of the plates. I could change the distance between them. As long as I haven't discharged it, as long as I have not emptied my bucket, the charge is the same. So that's also correct. The voltage is also the same. Literally everything stays the same. So the answer to this one was kind of a trick one. Literally every answer was correct. But for different reasons. Capacitance was the same because I didn't change the area and the distance between the plates. The charge was the same because I didn't discharge it. The voltage was the same because if capacitance is the same and charge is the same, voltage is going to be the same. Now, how would I change this problem to make it so that, process of elimination, the only one? I hook up a capacitor and fully charge it. I then disconnect a battery and double the distance between the plates. What stays the same? Only the charge. If you change the distance between the plates, you're changing the capacitance. If you're changing the capacitance, you're changing the voltage. If you're changing any of those, you're changing the energy stored. So, there you go. All right. So that's good to understand what a capacitor is. It's good to understand what changes what. Let's do one more with capacitors. Another conceptual one. Shown below, halfway between the two plates of a capacitor, the electric field is 3 newtons per coulomb, whatever. If I move 3/4 of the way between the plates, what is my electric field there? So let me draw a picture of this because this wording is not ideal, but here's my capacitor. The original electric field was halfway between it. Then the question is, what happens if I move up here? We'll call that point 2. What happens to my electric field if I move to some spot, and you know what? Let's just give you all more information so I can maybe confuse you more. Let's make this side positive and this side negative. So, take a guess, y'all. Remember the key to any of these problems, whenever I say something changes, what equation relates those things? Or, this one's what equation relates those things? That's always a good safe bet to go to. So if I think of capacitors and I say anything with electric fields, you should go to the equation for the electric field and a capacitor. That is E equals sigma over epsilon naught. Sigma is my charge per area. Okay, so I'm moved. I am farther away from the negative plate. I am closer to the positive plate. What variable does that correspond with? It's not Q. It's not A. It's not epsilon naught. So it doesn't matter. So what happens to my electric field? What's my electric field there? 3 newtons per coulomb. If the variable doesn't show up in the equation, who cares? Easy example of this. That may be related. What ridiculous example can I come up with? If the price of a dog in Alaska becomes twice as much, how does that affect your house, the value of your house in Florida? We're going to assume there's no correlation between a dog in Canada and your house here. Therefore, who cares? Remember, these equations tell you what actually matters. So what actually affects the electric field? The charge, the area, and this epsilon naught, which is just a constant. So, if you don't change any of those things, then you don't change any of those things. Then the electric field is the same. Okay? That is a possibility for nothing to change. Or for two things to change in such a way that they cancel each other out. Alright, so that kind of covers the gambit with capacitors. I guess one more capacitor question I could ask that's a good one. A capacitor has a gap, a distance between the plates of 3 millimeters, and has an electric field of 5 newtons per coulomb. What is the voltage? What is the potential difference between the plates? I.e. voltage. All right. So this is one of those. What is the relationship between voltage, potential difference, voltage, electric field, and distance between plates? Let me pull up the formula sheet. So what is the relationship between V, E, and D? There you go, y'all. See if you can find it. Nice thing with this formula sheet, it's in the order we learn things. So all the capacitor stuff is together. All the electric field stuff is together. So our capacitor stuff is in this general area. V equals ED. Again, you all are blessed. You don't, well, say blessed. Some would consider it deprived. You all may or may not know calculus. It is not a requirement. So you're blessed to not have to do calculus with this V equals ED. Technically, it should be an integral. But in an electric field, in the capacitor, it's constant. So V equals ED. Now, if you say the answer is 15 volts, you forgot to convert your units, so don't forget to do that. It's going to be 5 times 0.003, so it's going to be 0.015 volts. Do be careful with unit conversions, y'all. You best believe I'm going to make you convert your units, because the reality is that's how the world works. When you're measuring the distance to your house, no one's doing it in feet. Or, let's just put, no one's doing it in meters. Some metric units are funny. You measure things in different units because it's more convenient for certain things. If you want to measure how big, your hand is, you're not going to measure that in feet. You're going to measure it in inches. You will use an appropriately sized unit depending on your measurement. If it's really small, use millimeters. If it's really, really small, use micrometers. Really, 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 really small, nanometers. The reason for that? No one knows. I mean, if you can figure out how big this is off the top of your head, 3,345,637 millimeters. I have no idea how big that is in this unit because our brains can't do big numbers. It's a limitation to the human brain. The reason we have unit conversions is because your brain, in my opinion, how do you figure out what your brain can process? Literally imagine the biggest crowd you can where you can recognize the number of people. Can you imagine a crowd of, can you imagine a crowd of 100 people? And you can individually think of each person. Can you imagine a crowd of 500 people and imagine exactly kind of how big that would look? The second you get near 1,000, your brain just kind of, it all becomes a big blob. And what your 1,000 and someone else's 1,000, and you know, bigger. 10,000, that's just a horde of people. 10,000 looks the same. I have no idea what 10,000 people looks like. So that's why we have unit conversions. So for example, this would be 3.34 kilometers. And you can process 3.34 kilometers. You can have a sense of what that looks like. Just because it's a weird psychological thing that your brain can't imagine big numbers. So we use unit conversions to make it so we can. All right. Let's see. Was there... I'm trying to think if there's anything else with capacitors that would be relevant. Again, just know, hey, if I triple the area and half the distance, there was already one like that in our clicker problems, though. All right, anything else in this final 5 minutes, y'all? 6 minutes, technically. Anything else that you're like, I really hate this thing. Can you do that? Because that's how this works, right? No. Yeah.
Electrical potential energy, number 12 of Form 6.
Sure, let's check out what that one is. It is good. That was the other thing I was kind of thinking of. Should I do? So electrical potential energy. Scroll. Number 12. Yeah. All right, so what is the net? This is a good problem to do. What is the net electric potential at the top of the triangle, sir? So let's do this one real quick. And you know what? Let's vary it. Let's do one like it. Not that exact one, because that's already there, and some of you may have already done it. So let's put a charge here. Let's put a charge here. And let's find the potential. We're going to do two different locations. We're going to do here. We'll call that P1. And we're going to do here. We'll do one at a time. We're not going to do both at the same time. So let's call this distance R. Let's call this distance R. Let's make this one positive 5Q. Let's make this one negative 3Q. What is the potential at point R, or at point P? This is a good problem. I'm glad this is a good one to end on. What is the potential at point P1? So whenever you're talking about potential, we're going to use this. Go ahead and give that to y'all, save y'all a little bit of time. All right, I think doing this in my head that the answer is going to be this. But let me think through that a bit more before I commit. Yeah. All right, that is the final answer. So that's a check for those of you that are kind of working through it quicker. I will work through this, but this is a check for y'all if you're kind of ahead. That is what the final answer is going to be. So if you want V net, again, let's call this guy 1, this guy 2. V net is going to be V1 plus V2. V1 is going to be K 5Q over 2R, because it's not R away, it's R plus R. So the total distance from here all the way to here, that's 2R. And in fact, let's do one more step in here. I'm going to go ahead and call this, I think an extra step may just confuse it more. So that distance is 2R, because it's 2R away. Plus K, when it comes to voltage, you do put the signs in. I didn't write an absolute value when I wrote down these equations. It is very important that you all put the things in this. That's negative 3q over r. Now, how did I get the final answer? Least common denominator, y'all. Least common denominator is 2r, so that's going to turn this one on the right. But adding a negative is the same as subtraction. And we get our final answer. Okay. All right. So there you go. And then, let's do one last quick one. Let's call this point 2. Let's call this R. Let's call this R. What is the electric potential at point P2? So V at 1 was this. V at 2. How do I want to write this? 2kq over r. Again, I will work through that one in just a second. If I want the electric potential at point 2, same process, y'all. V net equals V1 plus V2 equals K 5q over r plus K negative 3q over r. Five q plus negative, they have the same denominator, so I don't have to do anything fancy. Equals positive 2q over r, kq over r. All right, that's it, y'all. I'll post this with all its reviewy goodness. Good luck with reviewing. I hope, again, my hope is at this point, y'all, that you've done the work and that when you look through it, you're like, yeah, I know how to do these problems. And if you can do the problems that we've done, the problem set, the quizzes, you should do awesome on this, y'all. Like, take that as your comfort. If you look through stuff, that means you're ready. That means you're going to do well. That is the way I have designed this class purposefully. So, hopefully that gives you some peace of mind. If you've done what you need to do, you should do great. Good luck. See you all Thursday. On Thursday, make sure you show up a couple minutes early because I literally a minute or two before that the class begins, I'm going to start passing out tests so you all get the full time because it always takes a little bit.
It's about the first one you do.
Sure. Let me stop this.